Let's take all this information and figure out how to sketch the graph of this function. We see that its highest power of x is 3, so it's x cubed, it's a cubic function. We should have some vague idea of what that looks like. Hopefully what we end up doing makes sense. So we remember that the function is increasing on the intervals from negative infinity to 1 and from 3 to infinity, decreasing from 1 to 3. We also figure out that we have a local max at 1 and a local min at 3. Okay. So that will be helpful information. And we just figured out that there's an inflection point when x equals 2. But we actually might benefit from some additional information. It might help to know what the y value is that goes with that. So I'm going to calculate the y values of all the important x values. We have 3 important x values. We have x equals 1, x equals 2, x equals 3. 1 and 3 are important because they're local extrema. Extrema is the general word for minimum or maximum. And then we have an inflection point. Let's calculate the y values that go with these. F of 1 is going to be 1 cubed minus 6 times 1 squared plus 9 times 1 plus 1, which should give us 5. To make my graph a little easier to read, I'm going to put some space between 1, 2, and 3. So this is 1, 2, and 3. I just learned that a point on my graph is 1, 5. So I will say that that's 5. Here's my point, 1, 5. Let's do f of 3 next because it's the other local extremum. We have 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. So we're going to have 27 minus 54 plus 27 plus 1, which will just be 1. That means we have the point 3, 1 on our graph. 3, 1 will be about there. And finally, f of 2, now we're going to get the y value of our inflection point. That'll be 2 to the 3rd power minus 6 times 2 squared plus 9 times 2 plus 1. That's 8 minus 24 plus 18 plus 1. And I believe that will give us 3. So I have the point 2, 3 on my graph. Okay. We're going to figure out increase, decrease, concavity, but we have it all here. It's all right in front of us. The function's increasing to the left of 1. It's decreasing between 1 and 3. But notice that while that decrease is happening, there's a change in the concavity. Between 1 and 2, the function is decreasing and concave down. But between 2 and 3, the function is decreasing and concave up. What does that look like? Well, let's do a little scratch work. decreasing and concave up. That's going to look like that. That would be this part here, between 2 and 3. What about between 1 and 2? It's decreasing and concave down. So decreasing and concave down would look something like this. That gives us an idea of what the function looks like at 2. So it's not going to be just a straight line connecting these 3 points. There's this subtle idea of concavity happening. Okay, remember we have a local max at 1, which means we're going to have a hilltop. And then at 3, we're going to have a valley because it's a local min. It's going from decreasing to increasing. So let's take that and finish the graph. Okay, local max at 1, inflection point at 2, still decreasing. Now we switch to increasing. And what we have here, just to check, is we have a concave up portion to the right of 2. That's consistent with what we have here. We have a concave down portion to the left of 2. That's consistent with what we have here. We are increasing before 1, decreasing between 1 and 3, and then we're increasing to the right of 3. So this is the graph of the function. We used the first derivative and the second derivative to give us enough information, along with a few important points that we calculated, to get a really, really accurate graph of this function.